This is Calculus 12, Chapter 5.4. We're going to learn about the fundamental theorem of calculus. And this is the heart of learning how to do integrals. So, Theorem 4, Part 1. Part 1 is not used quite as much as Part 2, but it's necessary to prove Part 2. If f is a continuous function on a to b, then the function capital F of x equals the integral from a to x, f of t, dt. So we don't want to confuse the function by having an x here and an x here. We want to know that the substitution is an x for a t. So this function has a derivative at every point x in a to b, and if we take the derivative, and we're taking the derivative of this integral, then it's just f of x. Okay, a doesn't matter what a is, we have just f of x. And as I have mentioned, the proof is long and difficult to understand, so just try to understand the theorem. And the second equation states that the integration and differentiation are inverses of each other. So we're integrating f of t, but we're integrating with the limit a to x. And then we differentiate the whole thing. We get back f of x. So that implies that they are inverses of each other. So let's look at some examples. So we need to take the derivative of y. So dy dx equals d dx integral from 0 to x cubed cos 2t dt minus integral from 0 to x squared cos 2t dt. Okay, so we need to split up this integral because it has two variables. Here we have a constant and a variable. So we need the constant as the lower limit, and we need the variable as the upper limit. So we split this up using additivity. And on the second part, it should be x squared to 0, but we're using the order property. So we're reversing the order of the limits of integration, and we negate the whole definite integral. Next, we want to use the fundamental theorem of calculus part 1. So we just put in this function 2, and we do our substitution with the limit of integration. That's x cubed. Now we have a function. X cubed is a function, and it's going inside another function, and that's a composition. And when we do a composition and we're doing the derivative, we need to use the chain rule. So d dx, x cubed. And similarly, we have the same here. Cos 2x squared d dx x squared. Now we can just simplify. This is 3x squared cos 2x cubed minus, and this is 2x, and cos 2x squared. And that's all we have to do. The main part is recognizing that this is a function and we need to use a chain rule. So let's look at another example. Dy dx equals d dx We're integrating from 0 to cos x t squared dt, and we're subtracting the integral from 0 to sine x t squared dt. Okay, we just substitute cos x for t, so this is cos squared x, and we need to use the chain rule. D dx cos x. We substitute sine x for t, so we have sine squared x. We use the chain rule on sine x. D dx sine x. Okay, fundamental theorem of calculus, part 1. Fundamental theorem of calculus, part 1. Now we just take the derivative. This is negative sine x cos squared x, and it's customary to put sine before cosine. And we have sine squared x. We're not taking the derivative of this, we're just taking the derivative of the limit of integration. So this is just cos x. And we're done. Okay, fundamental theorem of calculus part 2. This is the one we'll be using more frequently. If f is continuous at every point of a to b, and capital F is any antiderivative of f on a to b, then we have the integral from a to b f of x dx equals capital F of b minus capital F of a. Looking at the previous example, you can see how we're splitting it apart, and we're doing the fundamental theorem of calculus part 1, and we're doing the fundamental theorem of calculus part 1, so we're doing it twice. We're doing the same thing here. Fundamental theorem of calculus part 2 is also called the integral evaluation theorem. And the idea is this theorem lets us compute the definite integral without Riemann sums or calculating areas. All we have to do is figure out what the antiderivative is. Okay, so the antiderivative of sine is negative cos x. And then we write it like that. Lower limit, upper limit. So we use the upper limit first. Negative cos pi minus negative cos 0. Now we evaluate. Cos pi is negative 1 minus negative, and cos 0 is just 1. We have a minus negative 1 and a minus negative 1, so those are both positive. This is just 2. Let's look at another example. We need to factor this. 0 to 5. We have 3 plus x, and we have 3 minus x, and we have 3, and we have x minus 3 dx. So the problem is we have an NPV, and the NPV is x equals 3. So definite integral does not exist. Okay, that's because we have to have f being continuous at every point. So we have to be careful. If we plug this in on our calculator, and we ask it to compute the integral, it will be happy to compute the integral for you and not say that it does not exist. That's because it's calculating an improper integral, and we won't get to that concept till later. So for now, you just say it does not exist. However, if we want to calculate the integral from 0 to 2, this does exist. So it's the denominator is 3, so 3 times 2 plus 2 is 8. So this is negative 8 over 3. If we want to calculate it with antiderivatives, we simply take this, we cancel out this, make this negative because we're factoring a negative 1 out. So we have negative 1 over 3. Use the constant multiplier to move this out. Integral from 0 to 2. The antiderivative for x is x squared over 2. And the antiderivative for 3 is 3x. Sorry. And we're integrating from 0 to 2. And it'll give us negative 8 over 3. Negative 1/3. 2 squared divided by 2 is 2. Plus 3 times 2, that's 6. And 0 would just be 0. So we have negative 8 over 3. So a couple of antiderivatives that you should know. Integral x to the n dx equals x to the n plus 1 over n plus 1. Another integral you should know is a dx. A is just a constant, not a variable. We get ax, and of course we have to add c in there. But when we're doing definite integrals, you can leave the plus c out because it will cancel out. And that completes this lesson.